Imagine you're handed 150 flowers. For every flower, you have just 4 measurements: sepal length, sepal width, petal length, and petal width. And you're told that these flowers belong to 3 different species. The question is simple: can we use those 4 measurements to identify which species a flower belongs to? That's essentially the problem Ronald Fisher was investigating in 1936 when he introduced the famous IRIS dataset. And we're going to use this one dataset to explore 3 very different data science problems spread out over 3 videos. First, we know the species. Can we build a model that distinguishes them? Second, what if 4 measurements become 40 or more? Can we reduce the dimensionality and still classify the flowers accurately? And third, what if we don't know the species at all? Can we discover the hidden groups just from the data? So over this 3-part series, we'll go from classification to dimensionality reduction to cluster analysis using the same dataset throughout. And today we'll start with Fisher's original problem. Can 4 measurements tell us which flower we're looking at? And below is a roadmap we'll follow that will guide our data science walkthrough for the coming 3 videos. But before we get into the models, let's look at what we're actually working with. The IRIS dataset contains 150 flowers divided equally among 3 species: Setosa, versicolor, and virginica. And for every flower, we have 4 measurements: sepal length, sepal width, petal length, and petal width. So our dataset is essentially a table with 150 rows and 4 numerical columns, plus the species label. And that last column is important because we already know the species of every flower. This is a supervised learning problem. We're not asking the computer to discover groups. We're giving it the groups and asking them, hey, can you learn to distinguish them? But before building any model, there's a very important step that is sometimes skipped in data science tutorials. That is, look at the data. So let's start with some simple descriptive statistics. And let's also chart some box plots and compare means, standard deviations, minimums, and maximums. Already, we can see that the 4 measurements are on different scales and that some variables appear to vary considerably more than others. We know that they all have different centers and that petals have a wider dispersion across length and width just by taking a look at the boxes and how much longer they are versus those of the sepals. Now, let's try to visualize the data some more. We'll bring up the matrix scatter plot. And this is where things get interesting. Look at these scatter plots. Some of the variables appear to have very strong relationships. And more importantly, the observations don't look like one homogeneous cloud. We can actually see groups beginning to emerge. In fact, there's something rather strange going on here. If we calculate the correlation between some variables using all 150 flowers together, we can get one relationship. But separating the clouds by species using different colors shows a very interesting pattern where relationships can change dramatically. For these charts, for example, we use SPSS scatter plots, which by the way can also be done via Excel, except it involves several steps, while the SPSS software can do it much easier. So for our purposes, we'll just use the SPSS output like so. Now we see what happens if we ignore the species Setosa and take a look at the resulting trend lines. Some relationships totally reverse. Now, all the correlations are positive. This is a classic example of Simpson's paradox, but I won't dwell on it for now. Let's just park that idea in our head. Now, this raises a very interesting question. Should we be analyzing this group separately? Absolutely yes. There's a much bigger discussion here, but we're going to deliberately leave that question for later. Because remember, our problem today is the one Fisher originally posed. Can we use the measurement to distinguish the known species? That is, we already know the species beforehand and we're not trying to infer them from the visual groupings or clustering. So we'll come back to the issue of hidden groupings in part 3 under cluster analysis. But you might ask, why discuss this here if it's really part 3 content? Well, the reason we brought this up here is because when doing the data visualization part of your preliminary data analysis, you might stumble upon clearly demarcated groups visually. You might therefore be tempted to think that linear discriminant analysis, or LDA, is about distance of points, these groups or clusters. So let me stop you right there. It is not. Distance from groups is true of cluster analysis, but not true of LDA or linear discriminant analysis. More about this in part 3 when we get to cluster analysis. So let's formalize the problem with linear discriminant analysis. We have 4 measurements going into the model, x1, x2, x3, and x4, and we want to predict one of 3 possible outcomes, setosa, versicolor, or virginica. This is the classification problem, and Fisher's approach was to find combinations of the original measurements that would make these 3 groups as distinguishable as possible. That method became known as linear discriminant analysis, or LDA. Now, I'm not going to derive LDA mathematically here. We'll just use software for the computations. This is because we got a much more interesting question. What does LDA actually accomplish on the iris dataset? So now we go to the heart of the matter. How does LDA actually solve Fisher's problem? Remember, our goal is very practical. Given the 4 measurements of a flower, can we determine which of the 3 species it belongs to? LDA does this by learning the characteristics of the 3 groups from the flowers whose species we already know. Think of it as building 3 classification functions, one for each species. One asks, how well does this flower fit setosa? Another asks, how well does it fit versicolor? And the third, how well does it fit virginica? Each function takes the 4 measurements of a flower and produces a classification score. We don't need to get into the mathematics behind those functions. The intuition is simply that the score summarizes how well that particular flower fits the characteristics LDA has learned for each group. Now suppose we have a brand new flower. We know its 4 measurements, but we don't know its species. We run those 4 measurements through our 3 classification functions, and it might look something like this. We get 3 scores, and the rule is remarkably simple. The highest score wins. This determines our guess species. In this example, virginica has the highest score, so the model classifies the flower as virginica. Notice that we're not asking which species is geographically closest, or which one has the smallest distance. We're asking instead, which group does this flower fit best? The classification score is simply a numerical way of making that comparison. So best fit means the one with the highest classification score, and not the lowest distance from a group center, as you might have been tempted to think when you saw the clouds of data in the scatter plots. More on this in a while. So why discriminant analysis? You might be wondering, if we're talking about classification functions, why is this called discriminant analysis? Because before LDA can classify anything, it has to learn what distinguishes one group from another. It looks at the flowers we already know as setosa, versicolor, and virginica, and searches for the combinations of the 4 measurements that best discriminate or distinguish these groups. So discrimination is the underlying idea, while classification is the practical application. LDA learns what separates the groups and then uses that information to classify a new observation. So LDA discriminates or makes distinctions using a system of merits and demerits per given variable across the variable set. And the whole point is to rack up as many points possible across variables so that the highest score determines where the point is classified. It really discriminates with markups and penalties, as we shall see later with the numerical example. So let's put Fisher's model to the test and do an LDA. We take the flowers whose species we know, train the LDA model, and then ask it to classify the observations. We can compare its predictions with the actual species, and that gives us a straightforward measure of how well the model performs. Now, using standard LDA output from SPSS, we get 3 classification equations like so. For example, the first row of data containing 5.1, 3.5, 1.4, and 0.2 gets screened across the 3 classification functions, and so we have this. Because row 1 scores highest in function 1, therefore row 1 is likely a setosa. Now we do this for all the 150 rows and classify them accordingly. We then compare it with the actual species. For convenience, we will tag function 1 as setosa with a 0, function 2 as versicolor with a 1, and function 3 as virginica with a 2. We will now show the confusion matrix, where we compare the actual label with the tag we made using the classification functions. We mark in red where the functions got the classifications wrong and show which species it belongs to actually. And this is what it looks like. Setosa is particularly easy to identify. The more difficult distinction is between versicolor and virginica because their measurements overlap more. We all saw this via the scatter plot. Nevertheless, LDA does a remarkably good job of separating the three species. So if you got this far, congratulations, as you've done your first linear discriminant analysis using the iris dataset. From here on, you can measure a new flower and use this model that you trained on the original 150 points to discriminate and guess the species of that flower you came across with. And this is the power of supervised machine learning using LDA. By the way, for this particular model, the mistakes were 3 out of 150, giving an accuracy of 98%. Now let's transition to the broader data science lesson. We knew the groups beforehand. Therefore, the classification made sense. And because the groups were known, LDA could explicitly use that information to discriminate across the groups. Now here's a teaser for part 2. Note that we use all 4 measurements to do the LDA, and that leads directly to the question we'll tackle in part 2. Do we really need all 4? What if we could represent each flower using fewer measurements without throwing away too much of the information? That's where principal component analysis comes in. It seems ridiculous to reduce data since we have a small dataset with only 4 variables. But 4 is easy. What happens if our dataset has 40 variables? Or 400? Do we simply throw everything into the model? That's where things can get dangerous. Can we reduce the number of variables while keeping enough information to classify the flowers? That's where principal component analysis comes into play along with ordinary least squares regression. Then a teaser for part 3. Remember those clusters we saw earlier? There's an even bigger question. Everything we've done today assumes that somebody already told us there are 3 species, guys. But what if they hadn't? What if we don't know that information? What if all we had was a spreadsheet containing 150 flowers and 4 measurements with no species labels whatsoever? Could we look at the data and discover that there are 3 natural groups hiding inside it? That's a problem we'll tackle in part 3 with cluster analysis. If you like this video, kindly click like and subscribe to help support the channel. Also, you can check out my Ko-Fi page, and if you'd like to buy me a cappuccino, this will certainly help me a lot producing more videos like this. See you next time in part 2 of this series, and thanks for watching!